Let's do some examples involving the limit comparison test. What we have here is one that when we first discussed the idea of the direct comparison test, we couldn't do, but it was inconclusive because we couldn't get the directionality to go quite right. But let's show that how we can use the limit comparison test, and this becomes very, very straightforward. So when we do these types of things, one thing that's really helpful for limit comparison tests is to kind of compare it to a polynomial or when you have like a polynomial here, compare it to something that has the equivalent power polynomial. So or degree. So if I look at this is degree 1 polynomial. So what I'd like to do is say, all right, I want to compare this to, something like 1 over n, a first degree polynomial that's just very, very similar. So you just take the sequence and take the limit. You say, all right, the limit as n goes to infinity of this over that. So you take the sequence you have and the sequence you want to compare it to. Now this is kind of ugly, so what we're going to do is we're going to rewrite that as the limit n over 3n plus 4. Hopefully you feel good about that, right? We multiply top and bottom by n, that'll cancel, and then leave an n on top, multiply top and bottom by 3n plus 4, it'll cancel, and leave it on bottom. Now if you take a look at that limit, that's kind of an infinity over infinity limit. So this is a really good example to use L'Hopital's rule. We get the limit as n goes to infinity of 1 over 3. Well, now we have something that doesn't depend on n, so we get 1/3. Now the limit comparison test says, well these things, that's a positive value and it's finite. So these things diverge together or they converge together. So let's take a look. Well, that sequence right there is the harmonic sequence, or the harmonic series. The harmonic series is a well-known divergent series. So we know that this series diverges. And so limit comparison test is really powerful because, again, you don't have to work extra hard at it. You just pick a sequence that's a lot easier to figure out. Now this one's a little trickier because what we have is we have the square root of n cubed plus 1. Okay, we have the square root of n cubed plus 1. Now what we want to do is what I call the effective degree of the polynomial. The effective degree. What do you mean by that? Well, I know that this is degree 3. I know it's degree 3. But it's inside a square root. It's inside a square root. Well, so that tells me that the effective degree is n to the 3 halves. So that's the way you do it. If you write the root, like if it was the 4th root, you'd write the 1/4 power or whatever. And you just use the effective degree to make your life a little simpler here. Okay, well now that we have that, let's take a limit. So we take the top sequence divided by the bottom sequence. But again, that's pretty ugly, so we're going to rewrite that as that. Now, there's a couple ways to do this. Personally, I don't like doing L'Hopital's rule here because you end up with a chain rule and it's kind of ugly. I mean, you can. You're welcome to do it. I don't think it's a good idea though. So what I'm going to do is I'm going to use a little bit of clever factoring. So I'm going to say I've got this here. What if I factor n cubed out of both terms? Which seems kind of odd. But I'm going to say, alright, that's n cubed 1 plus 1 over n cubed. Okay? Hopefully you feel good about that, because that's just n cubed, and then that would cancel to get 1. Why would I do that? Well, because then I can apply the square root I can say, well, that's the square root of n cubed times the square root of 1 plus 1 over n cubed. Right, that's the definition of how square roots work. You can, if there's a product here, you can take the square root of each piece. But I know that the square root of n cubed is also n to the 3 halves. Okay, so now I have n to the 3 halves on top and bottom, so I can cancel that. So I have the limit as n goes to infinity, 1 over the square root of 1 plus 1 over n cubed. Why is this helpful? Well, I mean, as n gets large, n cubed gets even larger, so 1 over n cubed becomes, just vanishingly small. So you end up with 1 over the square root of 1, which is just 1. Okay, so what does this mean? Well, this tells me that I've picked a sequence for which, when I applied the limit, this is a positive number and it's finite, which tells me that I've picked a sequence that has the same end behavior. So now what I have to do is I have to say, okay, well, what about n equals 1 to infinity of 1 over n to the 3 halves? Well, if you look at that, that's a p-series because it's 1 over n to a power. And so I take a look at what this p is. Well, that's larger than 1. So since it's larger, since the power is larger than 1, it converges. So this one diverged, this one converged. So now we have to look over here. This one would be difficult with the direct comparison series because if you look at it, it's pretty obvious you want to compare it to 2 to the n over 3 to the n. It's pretty obvious you want to do that. But in practice, it's difficult because you would have to use a less than or equal to. But this is a prime candidate for like a greater than or equal to situation, and so is that one. So you wouldn't be able to apply the direct comparison. I mean, you could, but you'd have to work a little bit at it. But by using the limit comparison test, you can kind of get there without having to avoid that sort of spare chain, or without having to do some gymnastics to get around those nasty pluses and minuses. So what I say is, okay, well, I want to compare to 2 to the n over 3 to the n. So now what I want to do is say, all right, I'm going to take the limit as n goes to infinity, 2 to the n plus 2 over 3 to the n minus 4, all over 2 to the n over 3 to the n. When we manipulate this fraction, what we get is something like this. We're going to get the limit as n goes to infinity of 2 to the n, 3 to the n, plus 2 times 3 to the n over 2 to the n, 3 to the n, minus 4 times 2 to the n. So you end up with that kind of nasty little mess. Now, 2 to the n times 3 to the n is going to be just like a 6 to the n, right? That's how powers work. You have a to the x times b to the x. It's just ab to the x. So that lim, so that's 6 to the n plus 2 times 3 to the n. 6 to the n is 4 times 2 to the n. So then what you have to do is you have to do a little bit of extra effort here. This is kind of gross. Probably the easiest thing to do would be to factor 6 to the n out of everything. I know that's going to sound weird, but so we would do something like that. Now, once we factored out that 6 to the n, see those cancel, so I now have 1 plus 2 to the 1/2 to the n, 1 minus 4, 1/3 to the n. Now, why would I do that? Well, if I have 1/2, and then I multiply it by another half, it's a 4th, and then another half, it's a 8th, and then 16th, and 32nd, and so on and so forth. So we can see as n gets really large, the 1/2 drives down to 0. And the same thing happens with 1/3. As n gets really large, 1/3 drives down to 0, which gets us 1 over 1, which is 1. So what does that do? Well, okay, well now we know that limit is finite and positive, so we can we now have to evaluate this series and say, okay, does that series converge? Which is 2 to the n over 3 to the n, is just 2/3 to the n. This is a geometric series, and in this particular case, the geometric series that's r. We know that r is less than 1 in this case. The absolute value of r is less than 1 in this case, which tells me that it converges. And that's how you do it.